So for this question, we're told that 2 minus I is the root of z cubed minus kz squared plus 21z minus 20 is equal to 0, where k is an element of r and I squared is equal to minus 1. And our first task is to find what k is. Well, since we know that one of the roots is 2 minus I, if we substitute 2 minus I for each z shown here, the equation should equal to 0. So if we go ahead and say f2 minus 1 is equal to 2 minus 1 cubed minus k 2 minus 1 squared plus 21, 2 minus 1 minus 20 is equal to 0. And I'll expand out the brackets, so I have 2 minus 1 by 2 minus 1, that's 4, minus 4i minus 1 multiplied by 2 minus I again, so that's just 3 minus 4i by 2 minus I, and I get 6 minus 11i plus 4i squared. Well, that's just 2 minus 11i minus k bracket 3 minus 4i plus 42 minus 21i minus 20 is equal to 0, and minus 3k plus 4ki plus 42 minus 21i minus 20 is equal to 0, 2 minus 11i, dropping it down here. And then I'll go ahead and add together the constants first, just to tidy it up a bit. If we add these three together, we get 24. Then I'll add my terms with I together as well, so minus 11 here and minus 21, that's minus 32i, and then minus 3k plus 4ki. To tidy that up a bit, I'll group the real parts with the real parts and the imaginary parts with the imaginary parts, and we get this. And what we should do now is we should factorize this. We can factorize out the I, so we get 4k minus 32 bracket I, and then plus minus 3k plus 24. We'll go back to the top. We know that 2 minus I is a root, so therefore after simplifying and factorizing, we should realize that these two parts both have to equal to 0. So we can set these two equations up is equal to 0. 4k minus 32 is equal to 0. Minus 3k is equal to minus 24. K is equal to 8. And 4k is equal to 32. And then k is equal to 8. So we found out that k is equal to 8. And now the second part is asking us to find the other two roots of the equation. Well, going back to the question, it's told us that the first root is 2 minus I, so we'll just use the conjugate root theorem, and we can state that the second root is 2 plus I. But hold on, the equation here is the highest power z cubed, so there should be a third root. Well, how can we find that? Well, let's say z is equal to 2 minus I, and then z is equal to 2 plus I. Therefore, the factors, if these are the roots, we'll convert them to factors, which are z minus 2 plus I, and then z minus 2 minus I. Let's multiply these together. So we get, hold on, I'll rewrite it down here. Get z squared minus 2z minus zi, and then minus 2z plus 4 plus 2I plus zi minus 2I minus I squared. So we get z squared minus 4z, zi's cancel, and then 2i's cancel. Well, I squared is equal to 1, therefore minus I squared, I squared is equal to minus 1, therefore minus I squared is equal to 1. So that's essentially 1 here. So plus 4 plus 1, and that's just plus 5. So here, this is one of our factors. So our original equation that they gave us in the question was z cubed minus k. Well, k we found out to be 8, so minus 8z squared, and then plus 21z minus 20. And here it's just a simple case of long division. Need more space here. So we get z squared minus 4z plus 5, z cubed minus 4z squared plus 5z, subtract, we get minus 4z squared plus 16z, and then we divide again, so we get minus 4. So minus 4z squared plus 16, sorry, I forgot to drop down to minus 20 here. Z minus 20, subtract, and our remainder is 0. So that means z minus 4 is equal to 0, therefore z is equal to 4. And that is our our third root, essentially. So our z1 is equal to 2 minus I, z2 is equal to 2 plus I, z3 is equal to 4. And here we've solved for all three roots. Now, back to this part, you could have also used the fact that z squared minus sum of roots by z plus product of roots. If you use this formula, it gives the factor of f of z.